Hello everyone, I'm Bill.
I'm Lana.
Welcome to our channel. Today we are going to take a journey through the entire life of Earth. From its birth and all the way to its eventual death.
Okay.
It's a massive topic, so make it a little easier to understand. We're going to do something fun. We'll represent the entire history of Earth as a 24-hour day.
Okay. I feel like I'm going like lunchtime better, but sounds like a plan.
Sounds good. Now let's begin with Earth's birth. At 0 seconds, about 4.5 billion years ago, the Earth was formed. In those early days, it was a very different place. The surface was intensively hot. There was no water at all. Imagine a boiling, barren landscape, far from the world we know today.
So wait, it was boiling, there wasn't even land?
Boiling lava.
Okay, so no land. Got
No
it.
land. Fast forward to 45 seconds on our 24-hour clock, which is about 4.2 billion years ago. This is when the things start to change. The Earth was bombarded by countless asteroids and comets, and these cosmic visitors brought something very important: the water.
Yeah, I would hope we didn't have water, no. So they brought water or it was under?
They brought water from outer space. But the ocean that formed weren't blue or a clear ocean we think of today. They were black and filled with heavy metals and toxic substance.
So was it black because of those heavy metals and toxins? Or?
Yes.
Okay.
And it wasn't a place that life could live, at least not yet.
Well, yeah, it was probably still too hot.
Over the time, these heavy metals, things like iron, nickels, and uraniums, start to sinking in the Earth's core. And this sinking wasn't a simple process. You see, many of these metals, especially uraniums, are radioactive. As they sunk deeper into the Earth, they underwent a process called nuclear fission.
Okay.
This is a type of reaction that releases a huge amount of heat, and they're like a tiny but slow atomic bomb going off for over millions and billions of years.
So it just keeps going off?
Yes, spontaneously.
Okay.
And this constant release of heat made the Earth's interior hotter and hotter, and eventually turned the core into a molten liquid state.
So the core was already there, it wasn't formed based on those?
It's in the process of forming.
Okay.
The molten iron in the Earth's core starting to rotate as the Earth spins, and this generating a powerful magnetic field surrounding the Earth, and this is crucial because it's starting to protect Earth's atmosphere.
Okay, that makes sense.
Without this shield, the harmful UV radiations from the sun and cosmic ray would have bombarded the Earth and make it, as we know, impossible for life to form. But before we go to the life, there's one more big piece of puzzle. The moon.
Moon. Ooh.
The timing of the moon formation is still a little bit mystery, but we do know that it plays a huge role in creating conditions for life to emerge.
Okay.
The moon, especially in the early days, was much closer to the Earth, and these created massive tidal forces. And imagine the ocean being pulled back and forth and constantly moving.
So by tidal you mean like waves?
The waves, exactly.
Okay.
The waves. This motion helps mixing and moving around various chemicals and substances and that were on the Earth's surface and creating the right condition for life to form.
Okay.
But the tidal alone weren't enough. You see, many essential elements for life, things like carbons and nitrogens and phosphorus, those elements are buried deep underground.
Don't forget lipids. Wait, is that there?
Well, lipids is a molecule formed by those elements. Right now they're still in the elemental state.
Okay, got it.
And just moving the ocean wasn't going to bring these deep buried elements to the surface.
Okay.
This is where the key theory comes in. The Earth uranium reserve helps it. So those reserves, along with the geothermal heat from the Earth interiors help bring these buried elements to the surface, and then the movement of the Earth's tectonic plates and combined with the volcanic activities play a major role in making these essential building blocks available for life to form. How did these early basic building blocks life come to be? It's a bit of a puzzle, but it started with uranium. So in this primordial Earth, there were these massive reserve of uranium-235. Now uranium is very special.
So what's 235?
235 means there's an isotope of uranium that has radioactivity. Now this uranium is a very special metal because it can undergo spontaneous fission. And what that means is when starting to split it keeps going like a fire that burns and burns until you stop.
So it just keeps going.
Yes. But there's a thing. These uranium reserves weren't buried deep in the ground just yet.
Oh, so it was up
on the surface.
Okay.
Instead, they were a bit closer to the surface, and when they split, it generated a lot of heat, like ongoing nuclear reactors. But without the purpose of creating electricity, the real purpose was to heat up the underground water.
Oh, okay. Lots of heat comes into this, doesn't it?
Yes, it was a hot place. Now imagine this. When the underground water reaches to 100 degrees Celsius, it was starting boiling and erupt and sending hot waters into the atmosphere. And then it cooled down and fall back into the ocean and creating a continuous cycle that was essentially a giant natural water circulation system that brought elements from below the Earth surface up to the surface. And it's similar how modern nuclear power plant uses steam to generate energy. Except the cycle wasn't for power, it was for creating the right condition for life. What's fascinating here is that the cycle was crucial in making organic compounds. They're including fatty acids.
Oh, there's the fatty acids.
Amino acids, phosphoric acids, and they're all essential building blocks. The lighting and the distillation process help these elements combine. It wasn't just theoretical. We have actually seen this happen in the lab.
So some people actually did an experiment about this?
Yes.
Okay.
In 1953, two scientists, Stanley Miller and Harold Urey, conducted an experiment that simulated the condition of early Earth. They took the seawater, carbon monoxide, hydrogen gas, and ammonium. Basically, all the ingredients exist in the early Earth. They added an electric charge to mimic the lightnings, and after about a week of its constant distillation process, the water turns to red.
Oh, okay.
And then when analyzing the compounds in the mixture, they found amino acids, organic compounds that are crucial for life. It was a huge breakthrough showing that inorganic substance could actually form organic molecules under the right condition. So these fatty acids, amino acids, and phosphoric acids starting to come together in more complex form. And when the fatty acids combine, they form a oil film. And amino acids come in together to form peptides and eventually proteins. And nucleic acids and eventually form like RNA.
Okay.
And
wait, what's RNA?
RNA is ribonucleic acids. And this RNA was the next big step.
Okay.
So when these components combined, they could form a primitive RNA, which under the right condition could start self-replicating. Here's the big leap. This self-replicating RNA, when surrounded by a lipid membrane, formed the earliest form of life. This happened about 4 billion years ago, or about 1 o'clock a.m. on our 24-hour clock.
Well, yeah, 1 a.m.?
We only had 1 a.m.
Oh, gee.
But of course, this was a very primitive form of life, and just a single-celled organism, no bigger than a tiny speck.
So could we even see this speck?
No, you cannot see the cell.
Oh, okay.
Now, this brings us to the next important question. What exactly defines life? Well, scientists generally think life needs three key things. The first, it has to be distinct from its environment.
Okay.
For example, a drop of water in the ocean isn't considered alive because it doesn't have a boundary that separates from its surrounding. But something like a lipid membrane encase a drop of water that make it distinct. It's separate from everything else.
Got it.
Second, the life needs to be able to metabolize. That means you need to take in energy or materials from the outside and turn them into its own energy while also getting rid of waste.
Okay.
This is a vital cycle. And the third, life must be able to self-replicate and has to be able to making copies of itself. So if something meets three criteria here, we're generally considered to be alive. These three steps are the basics and essentials.
Okay, so these are very basic.
Yes.
And they haven't changed over the years? Like, no scientist has been like, oh, we're switching this?
There are different versions, but everything needs to start off with these three basics and then maybe more complex requirements.
Oh, okay. Got it.
But the most complicated part is be able to self-replicate. Think about it. You take some wood and grass and after several lightning strikes and distillation cycles, you somehow end up with a piece of paper. That could happen.
I guess. Maybe.
But that's not so wild to think about, right? But what if this paper, they start to replicate itself? That becomes a miracle.
That changes the game.
A self-replicating piece of paper made from wood and grass, that's like a printer that makes copies of itself. The one becomes two become four, and so on. It's kind of like a magic, but science magic.
Science magic.
This process of self-replication is the hardest part of the life's origin.
Oh, okay.
If this could happen naturally, we would have birth of Earth. And if it doesn't work out, then the life can't emerge on its own. This is the key mystery to life. The moment when something becomes truly alive. And here's something fascinating. All known life on Earth is made just 20 types of amino acids.
That's very specific. We know for sure there's 20.
Yes.
Only 20. Not 21, not
20, yes, just 20. But believe it or not, over 300 types of amino acids has been discovered.
They're just not in this.
They're just not in those 20. So why did life settle on just these 20 amino acids? This is a real mystery. It's kind of like how the English language using 26 letters, even though there are thousands of possible combinations. The life didn't have someone setting the rules for it, but yet still chooses these 20 amino acids to create everything. It's almost as if someone or something designed it.
So controversial. So controversial.
Yeah, a very strange yet amazing process. Now let's move to 2 a.m. on our Earth clock.
We moved 1 hour. Wait, what does 2 a.m. equal then? Where are we?
2 a.m. is 3.8 billion years ago. And we began to see the earliest form of Earth not just existing, but actively replicating.
So we have life.
We have life.
Yay!
These primitive organisms start to reproduce, but like any system, there were errors. The genetic mutations start to occur, leading to the variations and didn't quite follow the replication process perfectly. The RNA, being a single-strand molecules, they start to be combined with other variations of RNA to form a duplex DNA.
Okay.
DNA, as you probably know, is far more stable than RNAs, and that reducing the error in replications. It's like RNA realized its methods of copying itself wasn't perfect, So it evolved into a more stable and efficient system. The DNA system allow for far more stable and accurate replication. And it was a huge step forward. And this marked the beginning of the DNA-based life, what we now call prokaryotic life.
Okay.
These tiny single-celled organisms were the first true life form, and they were invisible to our naked eyes. So by 1 a.m. we have a simple RNA life.
Okay.
By 2 a.m. DNA life emerged. And these early forms of life didn't need to mate or gender, and they just replicates by themselves. Now let's move to 3 a.m. on Earth clock. The cyanobacteria. These little guys are called living fossils.
Okay.
So the earliest fossil of cyanobacteria we have found dated back to 2.2 billion years ago. But we think they were first appeared around 3.3 billion years ago. And then the cyanobacteria, they were the pioneer of photosynthesis. They were the first organism to harness the sunlight and release oxygen into the atmosphere.
Oh, so they really were, the first.
Yes. Now, oxygen, as we know, is essential for most life today. But back then, not so much. In fact, the early Earth was anaerobic organisms.
Well, yeah, they didn't have plants or anything really then, did they?
No, not yet. And meaning that life that hate oxygen and treated the oxygen like a poison. The cyanobacteria, they start to produce oxygen through photosynthesis, and these cause a huge shift. Many of these anaerobic organisms couldn't survive in this new oxygen-rich environment, and they're all wiped out. But here's the thing, the oxygen was a game changer for life. It allowed for much more efficient chemical reactions and producing far more energy than anaerobic process. And as we know, more energy means more complex life. Now let's move to 5 a.m., about 2.3 billion years ago.
That's a bit of a jump from 3 a.m.
Yes, it was. Which is when the Earth entered a major ice age.
An ice age?
Yes, ice age. And here's the twist. The ice age wasn't just caused by the Earth's own climate system. It was triggered by a cosmic event. The Milky Way collided with the smaller galaxies, which caused a huge burst of supernova explosions. And supernova are like massive, short-lived star that explodes and release gamma rays. These gamma rays hit Earth, cause water vapor in the atmosphere to condense and form clouds. As more clouds formed, they block the sunlight, then Earth begins to cool down rapidly.
Hence the first ice age. Hey friends, family, and everyone in between, thank you for watching the video here on FuseView. If you enjoyed it, please like, subscribe, and hit that bell so you don't miss any future content. Leave below a comment, thoughts, or questions. We would love to hear from you. Catch you in the next one. Bye!